I know it's like really early. Hi, how are you?
Okay. Whoa. We're kind of loaded up on this side over here. Well, first of all, thank you all for being here. I think we should have a quiz just for being here, don't you? Oops. Let me turn this off. Hello? Okay. Silence this.
No, I don't want your signature. You're gonna put C66 Yeah, sure. So that's why I'm like, you heard they have like
Okay, that'll work. All right, so first of all, I have a quick announcement.
someone's gonna fill the classes to me.
So exam 3, which was scheduled on February, March, April. What? We're in April, right? 18th is now the 12th. Oh man, this sucks, man. You suck. Wait, hold on. Hold on. It's the 11th. Sorry.
Oh my God.
We're not here on the 12th. Hold on. Is this right? The 11th.
Am I in the right class?
The 11th. So that is next Wednesday. Now, here's the reason why. Well, it won't have as much material on it, which is good. But the reason why is because there are quite a few students in here who don't know whether or not they want to drop the class. And drop date is, I believe, the 13th. And so if we have this test on the 18th, then you know, it's kind of too late at that point, right? So we're going to move it to the 11th. Are there any major objections to this? I mean, like if the whole class was like, no, let's do let's leave it at the 18th, then we'd leave it. But I mean, are y'all okay with this? So who would like to keep it on the 18th? Okay, that's all right. 1, 2, 3, 4, 5,
I kind of want to do it.
6, 7.
Wait, so it'll be less material, right?
It'll be less material. Okay, so let's see. Hands up high. Keep it the 18th.
Wait. Oh,
Keep it the 18th. I'm going to take a count here. 1,
I don't like
2, 3, 4, 5. What's that?
Several sections less?
Well, one section less.
What is it a hard one?
Curve sketching,
It sounds so fun.
which is long and tedious, but okay. How many of you want it to be moved to the 11th? Like, would like to? You voted these?
I'm not gonna say anything.
Okay. So wait a minute. 1, 2, 3, 4, 5, 6, 7. Just next Wednesday. I'm trying to make the test, give the opportunity to take the test before the drop date, in case then you have your third grade and you kind of know where you are at that point. So do you have a preference? Keep it at the 18th or move it to the 11th? Do you have a preference? Okay, so how many of you don't have a preference? Like you can't vote again. Just you either one or the other, but anyone? No? Okay, so that was like 50-50 almost. And I think the people who want it moved aren't here.
The 11th.
All right. Okay, let's do this. Let's plan for it to be moved. All right. Let's plan for this. I do want everyone to have an idea of where they are before the drop date with that third grade. All right. It'll be less material, so the test won't be. It'll only cover derivatives of exponentials and logs, L'Hopital, and max-min, mean value theorem, and derivatives and shapes of graphs. So, all right, okay, well, let's say this is official, all right? I apologize, but. Okay, so last week we were talking about finding the max and mins of continuous functions on closed intervals. So I wanted to pick up with that, do a couple of examples. Remember we ended class with that problem with the box where we folded up the corners, and you did that in class, you turned it in? Okay. I would like for us to take a look at this problem here. F of theta equals 2 sine theta plus cosine of 2 theta on the interval 0 to pi over 2. And the instructions here are to find the extreme values. That's it. So does anyone remember what we need to do? What? Take the derivative. And what do we do with that derivative?
Set it equal to 0.
Set it equal to 0. See if it doesn't exist. So two different things to look at. And those if it has solutions to being equal to 0, or if there are places where it doesn't exist, we call those critical numbers. And we take those critical numbers and do what with them?
Plug them into the original.
Plug them into the original function, and
plug in the
yeah, make sure those critical numbers live in here, plug them into the original function, and then plug in the two endpoints, and you compare all the answers. Your biggest answer is your maximum, global maximum, and your smallest value is your global minimum. So that's it.
They're in the domain first.
When you find the critical numbers. Is that what you're talking about?
Yeah.
Like whether or not they live in here?
Yeah.
Yeah, before you plug them in, you're wasting time. Okay, so let's start with the derivative. Is this a continuous function? Because we needed that. That was a condition to use this, what was this method called? The something method? Closed interval method. This is called the closed interval method for finding the extremum. Okay, so is this a continuous function? Well, is sine a continuous function? Yes, the sine function, draw it without picking up your pencil. And then the cosine function is also a continuous function. And when you add two continuous functions, you get a continuous function. So we have a continuous function. All right, so we take the derivative. We've got 2 cosine theta minus 2 sine 2 theta. So taking derivative of the 2 comes down, right? Derivative sine is cosine. Derivative cosine is negative sine of 2 theta, but chain rule says we have to then multiply by the derivative of what's in here, which is 2, and that's why there's a 2 out front. Right? So that's our derivative. We good? Now what we want to do is set this equal to 0. All right, so when we set this equal to 0, we get 2 cosine theta minus 2 sine 2 theta equals 0. And this, when I talk to my pre-cal classes, I tell them that there are like 2 major things in pre-cal class that I like my students to understand coming out. That's the unit circle, means knowing the values of the trig function along all the common angles. And then the second thing is solving trigonometric equations, which is exactly what we have here. This is a trigonometric equation, and we're trying to solve it for theta. And we're trying to solve it for theta just in this interval. All right, so how can we solve this for theta? We have a little bit of a problem in here because this is cosine theta, this one is sine of 2 theta. So they don't have the same arguments, right? This argument's different than this argument. So it'd be nice if they all had the same argument, right? Any ideas?
Identity.
Which one? You're on the right track. Are you saying some sort of identity that will get rid of this 2 theta for us? Is that?
Or like I was saying, like making it all like cosine.
Okay, so maybe get it all turned into things with cosine in. Okay, so I see you flipping there. Do you see any identities that would help us with any of this?
Is it like a power rule? Something like that?
We have a power reducing formula. We do have that. I'm not sure if that will fit in here. Well, the power reducing is when we have a power and we want to bring it down, like bring the power out. So yes, this is where you have to go and draw back on your pre-cal and your identities. So let's see who finds it first. What I'm trying to get is, I'll give you the hint that I'm trying to get this entire expression in terms of theta. I do not want 2 theta here.
Is it double angle?
Okay, double angle, which one? Because there's a couple. Sine 2 theta, there we go, that one. This right here. If you look on your formula sheet, you should have a double angle identity. I believe they use x, right, on there?
Yeah.
Okay, so the formula is sine 2x equals 2 sine x cosine x. Now, maybe now that you've seen that, you're reminded of it, and I hope that your pre-cal teacher told you that was a very important identity. It comes up a lot. It's coming up here today. So that is the double angle identity for sine. What that's going to allow me to do is replace this with 2 sine theta cosine theta. So I no longer have the double angle inside. So let me rewrite this. 2 cosine theta minus 2 times 2 sine theta cosine theta, like that. And yes, that 2 times 2 is going to become a 4, all right? Everyone see that? Okay, so let me just rewrite this. 2 cosine theta minus 4 sine theta cosine theta equals 0. And now I continue to solve. What can we do here? We have a greatest common factor. Both of these have 2 and a cosine. So I'm going to just pull a 2 cosine out, 2 cosine theta. And what would that leave me with here? 1 minus 2 sine theta equals 0. So now what I need to do is set each of these factors equal to 0. So I set 2 cosine theta to 0, and I set 1 minus 2 sine theta to 0. On the first equation, I can just divide both sides by 2, and I get cosine theta is 0. Right? Just divide both sides by 2. On this one, I can move the negative 2 sine theta to the other side, and then divide both sides by 2, and I should get sine theta as a half. Any questions on that? Okay, again, let's test our pre-cal knowledge here. Where is cosine 0? So this is asking you, where is cosine 0? Give me all the solutions. So this all goes back again. I don't know how your pre-cal class went, okay? But I know that my pre-cal students, I have a few of them in here, are going to recognize this when I do this. I draw a little unit circle, and I say to myself, when we deal with cosine, what we're dealing with is the x-coordinate on the unit circle. So this is saying, where's the x-coordinate on the unit circle? 0. And that happens here at pi over 2, and down here at 3 pi over 2. Those are the two places that it happens, right, on the unit circle. But I'm only supposed to look between 0 and pi over 2. So the only answer that I get from this is pi over 2. Now, that's it. It's pi over 2, right? But let's just check real quick. How many of you know how to write out the general solutions? So forget the rest of the problem, okay? If I just walked in today, put this on the board, told you, when is cosine of an angle 0? Like what angle will give you 0 when you plug it into cosine? How to write these as a general solution. Have y'all ever seen this? Like you start out, you say theta equals, and then you start out like at pi over 2. And then to get to this answer, you have to add pi. And then to get back up here, you have to add another pi. So you could say like start at pi over 2 and then add multiples of pi. And it's either k pi or n pi. Different books use it different. I used n in my classes. But so what this does is this tells you where to start at. You're at pi over 2. This tells you how much to jump by. So I'm going to jump by a pi, or 2 pi, or 3 pi, or 4 pi, and it gets you all infinitely many solutions. Now, you don't need that for this, okay? I'm curious to know if you're comfortable with that, because that will come up again later on, general solutions. If you are unsure about that, see a tutor or see me, I'll help you with that. All right, so the only answer we have here in this interval is pi over 2. And it turns out that that's an endpoint anyway, isn't it? Yeah. So I'm going to test that anyway, but I'm going to box it up because it's a critical number. All right, so where is sine 1/2? So whenever we deal with sine, we're looking at the unit circle, but now we're looking at the y-coordinate because it is sine. And you have to know that there is the common angles. This is an important y value. It happens here, and it also happens over here. And what is the angle that corresponds to that? 30 degrees, or pi over 6, and then the angle over here is 5 pi over 6. So those are your two angles that correspond to your y-coordinate being 1/2. So like I said, I tell my students two most important things: understanding the unit circle, solving trigonometric equations. This is both of them appearing in the same problem. This is why I tell them that, all right? So, all right, do these guys live in here? Pi over 6 does, right? So I'm going to scrap this one, right? Scrap that, and then I'm going to keep this one. All right, so we have gone through the process of taking the derivative, setting it equal to 0, and finding the solutions that live inside this interval. We then need to look and see, is the derivative ever undefined? So was the derivative ever undefined? So here's the derivative, right? I'm going to just take that 0 out of there. That's the derivative. Are there any thetas that I could plug in that would cause a problem? Well, cosine is continuous, right? This is a nice, well-behaved function. Sine of 2 theta is still just a sine function. So together, this is still a good function. We don't have division by 0. We don't have roots of, square roots, so you get negatives under roots. This is all real good, right? So when I ask myself the question of where is the derivative does not exist, or did I say undefined or does not exist last class? Does not exist? Okay. Does not exist. This was a question. Is this possible? Is this going to happen? No, so we just move on. So now, what are the critical numbers that I'm going to use here? Pi over 6 and pi over 2, right? So I'm going to take those and I'm going to plug those into the original function. And I also need to plug in the endpoints, right? The endpoints are 0 and pi over 2. I'm only going to do 0 because I'm already doing pi over 2. So just keep in mind, these two were critical numbers, and this is an endpoint. One of the two. All right, so now we get to plug these into the original function and see what we get. So I'm going to do 2 sine of pi over 6 plus cosine of 2 times pi over 6. Let's work that out. So what is sine of pi over 6? So you're looking at the y-coordinate at pi over 6. So 1/2, right? Times 2? 1. So this is 1 plus, all right, now what is 2 times pi over 6? Pi over 3. Now pi over 3, if you don't remember, pi over 3 is right up there. So cosine is the x-coordinate. So this is saying, what's the x-coordinate at pi over 3? And that's 1/2. So you get 3 halves here if you put it together. That's what you get. Is that good? Okay, now we need to do pi over 2. So 2 sine of pi over 2 plus cosine of 2 times pi over 2. And sine of pi over 2 is the y-coordinate at pi over 2. Pi over 2 is straight up, so that's 1. So this 2 times 1 is 2. Plus, all right, these 2's cancel, so you get cosine of pi, which is the x-coordinate at pi. Here's pi. The x-coordinate there is -1, so you get -1 here. So this is 1. Are you all following? And then finally 0, 2 sine of 0 plus cosine of, well, 2 times 0 is going to be 0, so. Sine of 0? Sine, that's the y-coordinate at angle 0. 0, so that's 0 plus 1. Because cosine of 0 is 1. So you get 1. All right, what are the extreme values, all right? The maximum is, what is the max? What is the maximum of this function on that closed interval? 3 halves. 3 halves. So yes, we do want to know where it happens, but the value is what we are really interested in. All right, so when we go to say the extreme values, I'm going to say the global max, I'm going to write f of pi over 6 is 3 halves. See, now I write it like this, I told you all last time, because I like to not only know what the maximum is, I'd like to know where it happens. All right? Now, what about global minimum? There's 2 places it happens, right? So what I'm going to say is, watch how I write this. F of pi over 2 equals f of 0 equals 1. See how I wrote that? What I'm saying is, at pi over 2, you get the same value as you get at 0, and that is equal to 1. So your minimum value is 1, but it happens at 2 different places. Make sense? Okay. All right, so that was a good problem because we got to play with some trig, right? Let's do one more, and then I think I'm ready to move into the next section. We're going to take the function f of x equals x times e to the negative x squared over 8. And we're going to do that on the interval -1, 4. That's kind of a weird looking function, right? There's a couple of different ways you could write that function. If you're having trouble looking at that and just thinking, wow, that looks weird, just keep in mind that that's the same as this. Right? Isn't that the same thing? Okay. We could also write it like this. X over e to the positive 1/8 x squared. I'm just showing you that these are the same expressions as this, right? All right. Because we have to take derivative, we might need to really be sure that we understand like other ways to look at this, right? All right, so let's try this derivative. Oh, well, is this continuous? We didn't talk about continuity of this. I think this one's probably the easiest one to look at and see that we have continuity. Because the numerator is just x. X is a line, okay? It's continuous. E, exponential function, should look something like this, and that is continuous everywhere, right? Now, the only thing we could possibly have that would cause a problem then is if this was 0. Because if this was 0, wouldn't this be undefined?
Yeah.
Okay, now can e to something ever be 0? No, because the nature of e raised to any power can never be 0, so you're never going to get division by 0. So this is actually continuous everywhere, right? No problems at all. So we are good to go with the closed interval method here. So I'm going to take my derivative. Now, which one of these do you want to work with? Would you like to work with, I'll give you these two options. Don't y'all like this one more? I like this more than this, because if I ever have to take derivative of this, it's easier for me to see the 2 pops out and then, it's no problem. Here, I've seen people try and do quotient rule on that, and that's just too much work, all right? You could do quotient rule on that, but it's way too much effort. Have y'all ever seen that? Let's look at it, because it's ridiculous. I see it happen too many times. Let's say we have negative x squared over 8, and I want to take the derivative of this. I could do derivative of the top, which would be negative 2x times the bottom, 8, minus the derivative of the bottom times the top over the bottom squared, okay? And so what winds up happening is this is gone, right? You have an 8 here that cancels with that 8, and at the end of the day, you're left with negative 2x over 8, which turns out to be negative x over 4. Okay? If you had instead just written this as negative 1/8 x squared, then take the derivative, the 2 comes out, 2 times negative 1/8 is negative 1/4, and you reduce the power. So much easier, right? So when I see a student do this to this, I'm like, yes, they understand quotient rule, but they really don't need that, and that means they're missing something that's even more important, that you can rewrite it to something easier. So, all right. So going back to this, taking the derivative, I think I want to do, I don't know, which one do you want to do? I don't care. If we do this, it's a product rule, right?
No.
If we do this, it's a quotient rule. So, you want to do the product? Okay, let's do product. Now remember, we have to set it equal to 0, right? Okay, so let's take derivative of the first one, 1, times the second, plus, right? The derivative of the second one. What's the derivative of e to anything?
Itself.
Itself, right? E to negative 1/8 x squared. And then chain rule times derivative of what's up here, right? Which we just did, negative 1/4 x. So I'll put it in parentheses, negative 1/4 x. And that's it?
Nope.
Nope, we still have to multiply by the first function, which is x. And let's clean this up. This is e to the negative 1/8 x squared. And then when I put these two together, I'm going to get negative 1/4 x squared. I'm going to slide that to the front and make this a minus 1/4 x squared. And then I'll still have the e to the negative 1/8 x squared. Y'all agree? All right, there's my derivative. And I have to set this thing equal to 0. Yeah, I've got a GCF that I can work with. So now I set my derivative equal to 0, which means that, let's go ahead and pull that GCF out now. All right, since they both have this E thing in it, take that out, and what would I be left with? 1 minus 1/4 x squared, and that's equal to 0. And then I set each of those factors equal to 0. Questions? Sure? So I'm going to set e to the negative 1/8 x squared equal to 0. Then I'm going to set 1 minus 1/4 x squared equal to 0. How about that first equation there? Is it ever possible to have e to something equal 0? No, no solution here. Okay, this is not ever going to be 0. Another way you could show that is just by doing this. You could take natural log on both sides, because wouldn't the natural log kill off the e? And that would just leave you with the negative 1/8 x squared. So you'd be like, yes, I'm going to start solving for x here, but when you do natural log of 0, it's undefined. Yeah, it's undefined. So that you know right away that something is wrong. All right, so this has no solution. This does not equal 0. And so we don't have to worry about that. The other one is just a little quadratic. You can just move that negative 1/4 x squared to the right. Then you can multiply both sides by 4. And then you take the square root and you get plus or minus 2. And only one of these lives in that interval, right? X is 2. We have, so far, just one critical number, right? Just one? All right, so let's take a look at when the derivative is undefined, because it might be. Let's see. Or when it doesn't exist. So the derivative does not exist. Question? Well, here's my derivative, right? If I'm covering up the 0 because I want to look at the derivative, not set equal to 0. So if I look at this, this is always defined, isn't it? Right? No division by 0. And this number right here is always a positive number, right? So this is never going to be division by 0 or something like that. So we're good to go. So this doesn't happen. Nope. So now it's just evaluate the function. Okay, so we're going to go f of, let's go 2, and then our endpoints, f of negative 1 and f of 4. So let's plug in 2 first. We're going to get, and we're plugging in here, right? 2 e to the, so negative half, right? Because 2 squared is 4, so negative 1/2. All right, next one, we get negative 1 e to the, what is it? Negative 1/8. See, because when you plug in negative 1 here, you square it first and it becomes positive 1, then you subtract it. And then when we plug in 4 e to the negative 2. Now that's kind of tough to see which one of those is the biggest and smallest, right? Let me rewrite this. This is 2 over root e. Ooh, that's what that is? Negative 1/2, drop down is positive 1/2. And then raising something to the half is the same as taking the square root. So that first one is that, right? The second one, if I wanted to do something similar, is like negative 1 over the 8th root of e. And then the last one is 4 over e squared. Now look, I already know one of them, like the absolute max or min. Do I know the absolute or global max or min? Do I know one of those right now? Just without a calculator, do I know?
The bottom one,
Is this positive or negative?
it's positive.
Negative? Positive, right? So this is your min right here,
That's your blue.
right? That's your global min because it's negative. All right, now the other two, I don't know. Which one do you think is bigger?
Bottom.
Think this one's bigger or this one? I think it's going to be the top one. Now this is the reason why. 4 divided by E is about 2.7. 2.7 squared is going to be bigger than 4. So 4 divided by a number that's bigger than 4, this should be less than 1, shouldn't it? This should be smaller than 1. This is 2 divided by the square root of 2.718 is smaller than 2. So 2 divided by, that should be bigger than 1. Anyway, you can get your calculator out. This one is your global max. You can do a decimal to confirm it. And this one right here is your global min. I'm not going to rewrite it. What I normally would write is global max is f of 2 equals that, and global min is f of negative 1 equals that. Are good? So those two problems that I just gave you give a good kind of sample. The first one is some trig stuff. This one had some exponential stuff. You know, you just have to be able to solve some equations, test some points. But the process, the procedure is pretty straightforward, right? Check for continuity, derivative, set equal to 0, where does it not exist, plug in, chug, right? Okay, let's move on. Let's move on. Do you feel like you have enough there to do the section? In the homework, there are two different major groups of problems in that homework set. The first one, they give you functions and they ask you to just find the critical numbers. That means they do not want you to do all the testing of points. They just want you to find the critical numbers. So you're practicing taking the derivative and setting it equal to 0 and finding out where it doesn't exist. The second section of problems in there, you take it the whole way like I just did. So just realize that there are two different things they're asking for. All right, so the next section, I'm not going to show it to you yet. I want to do something first that's related to it. So I know some of you are really good with your graphing calculators. So I would like to see if perhaps anybody on their graphing calculator knows how to solve this equation. Does anybody know how to solve? If you think you do, you can try it. I don't see many people going for their calculators. I see a few. I don't expect that you can do this. I just know that some of you can. I'm hoping that you're trying to use the solve function. Are you trying to use the solve function on there? Or are you graphing it? No? Does anybody know that there's a solve function on your calculator? Yeah? Okay. All right, well, here's another way you could use your graphing calculator to solve this. If you take this equation and move the x to the other side, add x, then what you're saying is where does cosine x hit x, right? So if you were to look at it graphically, if you graph cosine x, that's cosine, right? And you were to graph the function x, which is the diagonal, then they hit each other, don't they? They hit each other at some point. And most graphing calculators have an intersection function where it will find the intersection of these two graphs, and it'll give you the decimal answer. So have we been unsuccessful? No one's been able? I'm going to do it I'm going to watch you here. Go back to your graph. Go to calc. So you have to hit the blue button first, and then go to intersect. And then ask for a first curve. Yeah, hit enter. Second curve, hit enter. And then guess, try it. What does it say? Point the x coordinate. It says x is 0.73, right?
Continue.
Yeah, go a couple more.
908.
908. Okay. So this is using the calculator to solve this equation. All right? We get a decimal. Now, most of those calculators also have what's called a solver, where you could have just typed this equation in and it would have solved it and given you the same answer. This was using the graphing utility to get it. All right? So the reason I'm doing this is because I want you to now know what just happened in your calculator. All right? Like, how did your calculator come up with this answer? Right? That's a reasonable question. Like, how did it come up with this? Let's first appreciate how difficult this problem is. So let's go back to this. Let's go back to this right here. If I asked you to solve that equation, you would not be able to do this by hand. It is not possible to solve this in a closed form like this. There's no algebra. There's no trick I can show you, some advanced algebra that you were never shown to solve this problem. There's no way to isolate x without having it in terms of itself. Right? So I can't factor an x out, or right? There's nothing I can do. I could try and get the x out of here. How would I do that? How could I get the x out of the cosine? I do arc cosine? So if I did arc cosine over here, I'm like, haha, I'm going to be tricky. And I'm going to do arc cosine, will kill it off, right? But I have to do arc cosine on the other side. So it frees the x up here, but now it traps the x inside of this arc cosine function. So you don't have a way of freeing the x. Get it? So we have no way. So how did the calculator do it? I mean, is it that much smarter than us? Is it that much smarter? So what does a calculator know how to do? What can a calculator do? Maybe we should talk about that. Numbers? But what? What can a calculator actually do? I mean, it's amazing when you think about your phones, the web, everything that we do on our phones. All a computer is what? Zeros and ones. That's all it is. It's actually just, if you look at it a little bit deeper, it's on or off.
Yep.
That's all it is. You either have an electrical signal there or you don't. Okay, if the signal's there, it's a 1. If it's not, it's a 0. So it's binary. It's all basically yes and no checks. It's either yes or no, yes or no. Now, your calculator can do addition, subtraction, multiplication, division pretty easily. It can do it a lot faster than you can and I can, right? And it can do it without making mistakes. Yes? So it can check, it can test things like yes or no, true or false, and it can also do basic arithmetic. That's all it knows. It doesn't know that the cosine function is some, graph. It doesn't know that. So how is it getting to this answer? I'm going to show you, and that's why the next section is so important, all right? So I'm going to leave that up here. Here's what the calculator does. The calculator says this. It takes that idea right here. Now, you have to understand that cosine later on, okay, in Calculus 2, you will learn that cosine function, the way your calculator sees the cosine function is not the way you see the cosine function. It actually sees the cosine function as this function. 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. If you don't know what these factorials are, don't worry about them. But it looks at this as what we call an infinite series. But these are all powers of x. So if you type into your calculator cosine of 30 degrees, first of all, it has to convert 30 degrees over to radians, all right? And then, so let's say it's 0.2 radians. Then it's going to just plug 0.2 in here. Oh, here, let me get this. What's cosine of 0? 1. If I look at this expression, if I plug 0 in for all these x's, what happens? I get 0, 0, 0. You have to assume that this pattern continues, right? You get 0, 0, 0, and you're left with a 1. Okay? If you plug in cosine of pi over 2, cosine of pi over 2 straight up, you should get 0, right? So if you plug in pi over 2, you do 1 minus pi over 2 to the 3rd power over this, pi over 2 to the 5th power over this. This will subtract something, then add, then subtract, then add. And what happens at the end of the day is you get 0. It adds up to nothing. So anyway, what I'm getting at, I'm way off topic a little bit here, is that your calculator does not understand cosine to be this. It understands it to be this. So this is what we call the power series. The power series for cosine. And there's a power series for sine. There's actually a power series for e, too. I think I want to show you that. But what's really cool about this, do y'all remember being taught in pre-cal that cosine is an odd function and sine is an even function? Do you see why it's an odd function? Look at all the powers. They're all odd. That's not a coincidence. That is a defining property. And if you were to look at the power series for sine, well, I'll just give it to you. It's x squared over 2 factorial minus x. Yeah, well, yes, but I'm trying to remember if it's negative first, then positive. Who cares? You get the idea. So it goes like that. Okay? So it's all even. So when you type in sine of something on your calculator, it's doing that. Now, your calculator can't go forever. So there's some built-in into the program, it says stop at a certain point. So maybe it goes the first 20 of these. That's why we get decimal approximations, because that's the answer from the power series cut off at a certain point. And within the modes on your calculator, you can tell it how far to go. I think it says float. There's a float in there where you can tell it like how many decimals you want it to calculate to. So if you go like float 5, it's going to be super fast. If you go float 20, it's going to take a little longer for the calculations. Anyway, let me show you E, because E is mind-blowing. And then we got to get back to this. I'm sorry. But check this out. This is one of the most beautiful things. All right, this is the power series for e to the x. Hold on. I don't deal with this very often. 1 plus x squared over 2 plus x cubed over 3. Let me do it this way. 2 times, no, I'll do 3 times 2. 3 times 2 plus x to the 4th over 4 times 3 times 2 plus x to the 5th over 5 times 4 times 3 times 2 plus x to the 6th over 6 times 5 times 4 times 3 times 2 plus dot, 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 dot. Y'all see that? Yes? So what's e to the 0? What's anything to the 0? 1. So if you plug in 0 for all these x's, you get 1, right? Okay, what's e to the first power? E to the first power is e, right? About 2.718. So if I replace this with 1, 1, 1, 1, 1, 1, then you'll get, let's see, 1 plus 1, which is 2, plus a half, plus a 6th, plus a 24th, 1/24th. If you were to start doing that on your calculator, 1 plus 1 plus a half plus a 6th plus a 24th, I bet you you're going to be close to 2.718. And the further you go, the closer you get to 2.718. All right? But here's what's mind-blowing about this. What's the derivative of e? Itself. So let's check it. What happens if I take the derivative of this? What is the derivative? What is the derivative? Well, let me leave this up here. What is the derivative of 1? 0. Okay, so that's 0. Plus, what's the derivative of that? 1. Plus, what's the derivative of this? So 2 comes out. 2's cancel. You get x. Plus, here, 3 comes out. 3's cancel, and you get x squared over 2. Plus, 4 comes out. 4's cancel. You get x cubed over 3 times 2, right? Did y'all see what's happening? This is this. Right? It's just kind of moved over 1. 1, x squared over 2, x cubed over 2 times 3. That is a beautiful function right there. I know, I'm going way off. I'm sorry. It's hard to keep me away from this now. I didn't tell you what the factorial meant, right? But it's this. What I'm writing down here is what factorial means. So I'm rewriting cosine. Okay, check this out. This is what I said cosine was. Right, that's what I said what cosine was. What is the derivative of this?
Cosine was to the
Yeah, that should have been 7. Sorry. 7, 7, 6. Okay. So let's just take the derivative real quick. If I take derivative of this, 0. Derivative of this, 3 comes out, it'll be negative, right? And then 3's cancel and you get x squared over 2. Next one, 5 comes out, x to the 4th over 4 times 3 times 2. And so I wrote up here a second ago what sine was, right? Sine was x squared and then minus this and then plus. So this is sine, but it's negative. Oh, well, that's a derivative of cosine, right? Negative sine. Okay, so power series, chapter 8, Cal 2. Exciting stuff. So that's what your calculator sees. It sees power series. So, back to this. What your calculator does is this. It says, all right, I'm going to take two numbers that are very far apart, and I'm going to plug them into this and see what happens. So it knows we're trying to solve for 0, okay? It knows we're trying to solve for 0. It looks at this right here as a function, f of x. All right? And it takes two numbers and it plugs them in. Now, again, it's pre-built into the program. Usually it's like 1 with 99 zeros or something like that. So a huge number on one side and then negative 1 with 99 zeros. Two big numbers. And what it does is it just plugs them in and sees what it gets. I'm not going to pick two big numbers. I'm going to pick two small numbers. I'm going to pick, let's do 0 and 1. Okay? That'll be easy because we actually know where the solution is, don't we? So I'm cheating a little bit. So it plugs in 0 and 1. You think your calculator can plug in two numbers quickly? Absolutely. It can do that fast. And it can calculate that power series out, maybe 20 of those powers real fast. So let's plug in 0. What happens if you plug in 0 into this? Cosine of 0, 1 minus 0. So you get 1, right? Okay, great. Now, what's cosine of 1 minus 1? So I need somebody in radian mode on their calculator to plug in cosine of 1 and then take away 1. Tell me what they get. Negative 0.45. Y'all with me? Okay. I'm going to keep that up there. This is very profound what's about to happen here. So here's what your calculator is actually not thinking, but if we wanted to look at it like thinking, here's what your calculator knows. At 0, what was the value of this function? 1. So it knows, because it got a positive answer, that you're up here, right? And then it knows that at 1, you got a negative value. You're down here. So your calculator is now saying, look, between 0 and 1, my graph has to go from a positive number to a negative number, right? So that graph, somewhere in between here, has to go through to here, right? Connect the dots. I must cross through 0, right? So there must be a solution to this, so long as this is what? Continuous, right? So long as this is continuous, I should be able to draw from here to here. That doesn't give us the answer. It just knows that the answer is in here, right? So now here's what it does. It says, let me guess. Let me go halfway. Okay? So let me go halfway. So now I'd like, on the calculator again, for someone to plug in f of 1/2 is cosine of 1/2 minus 1/2, and tell me what you get. No? Yes, yes. You get 0.37, okay? So this comes out to be 0.37. But your calculator just cares that that's positive. So it says, okay, it's a positive number. So now your calculator has like, it's a flow chart basically. Your calculator is running a little algorithm. It says test 2 points. If there's a sign change, cut that interval in half. Now, do we have a sign change here? No, dump it. Do we have a sign change here? Yes, do it again. Cut it in half. So half of that would be 3/4. So plug in 3/4 into that, and what do you get if you plug in 3/4? So 3/4 gets plugged in, you get negative what? 0.01. Ah, okay. So it knows that it's in here now, right? Because this, at 0.34, you got a negative number out. So we have a sign change in here. Then it cuts that in half and does the same test and keeps cutting in half and half and half. And it starts to get that interval down really small. Really small. Like where the difference between the two numbers is like maybe 0.73906, let's say 7. Let's say that's one endpoint. And then the other endpoint is 0.73909. And it knows that this was positive and this was negative. Do y'all see what I'm saying? And now it says, okay, at a predetermined distance. So the calculator will say, look, if the distance between these two numbers is small enough, stop. And spit back the number in the middle. And that is an approximation. And there's your answer. Okay? So this is not an exact answer. This is an approximate answer. You want it to be better? You tell your computer to continue to cut. Your program that's built in will have to continue to cut more. This is called the bisection method. All right? That's called bisection. So any computer science program, or any computer science majors? I mean, this is a very simple algorithm to implement. Very simple algorithm. The problem with this algorithm is that it's slow. Even though our calculators can do it very quickly, we don't even notice it. We just, like you just typed in intersection, right? When it found it quick, right? So, but in more complicated problems, this would slow a computer down. So there are faster methods, one of which we will cover that's in this chapter that deals with a method called Newton's method, which is much faster. So this will get to the answer, but it's a high operation count. Newton's method will converge to the answer faster. Okay, all of this that the computer did, right, relies on what the next section is about. It's called the mean value theorem. Well, I should restate that. That's not what I meant to say. Sorry. Newton's method later, okay? Newton's method, which is coming up, relies on what I'm about to give you to be able to do Newton's method. You can't do Newton's method without the next section. But we use it to solve equations on computers. The mean value theorem, that's where we are. Okay, so let's take a look at this. We're in the mean value theorem. We actually start out, to do the mean value theorem, we actually start out with another theorem that's a little bit easier to see at first, and it's called Rolle's theorem. All right, so it says let f be a function such that f is continuous on a and b, on the interval, closed interval ab. I can draw without picking up my pencil, okay? That it's differentiable on ab. Now, notice the difference between this ab and this ab. What's the difference? Don't have to be differentiable at the endpoints, okay? But you have to be continuous on the entire interval. All right? And the third condition is that f of a equals f of b. That means the function